All right, so let's say you've got your velocity time graph, and it looks something like this, right? Label this velocity, centimeters per second, time in seconds, all right? And your intercepts were really close to 0, so I'm going to pretend they were 0. I wonder what the area under your velocity graph, what it means. Well, make up some numbers here. I'll make this 2 seconds, 100 centimeters per second. So to calculate this area, you would simply take 100 centimeters for 1 second, multiply 2 seconds, and you would get, what, 200? And the seconds cancel, that's 2 seconds over 1. So you're left with 200 centimeters. I wonder what this means. Well, what was the area under a velocity graph in the last unit? I think it was measured in centimeters. This would be a change in position, otherwise known as change in x. In other words, final position minus position at 0 seconds is 200 centimeters in the positive direction, because this number here is positive. Okay? Because we could have the same graph like this, in which case we would have a negative displacement of 200 centimeters. All right? So now you wonder what happens if we don't have an initial velocity of 0. Okay? This happens quite a bit, actually. So if you don't have an initial velocity of 0 centimeters per second or meters per second or whatever it may be, the graph will simply shift upwards. So you have some initial velocity v, you'll have final velocity, you'll have time on this axis, I'll write velocity, time here, and I'll call this time t, draw a dotted line up to correspond with my final velocity. Okay? And if you notice, our triangle is now a triangle plus a rectangle. So how would you find the displacement then? Well, let's do it. So the red rectangle, that displacement is going to be initial velocity times time, right? The blue area is actually a triangle, so I'm going to take this difference between my final velocity and my initial velocity. I'm going to add my triangle to my rectangle, okay? So I got 1/2, because this is a triangle, final velocity minus initial velocity times time. So this is the area of the triangle, and the red is the area of the rectangle, okay? And we know that this has to equal our displacement, okay? So what do I do next? Let's make it look nicer. This part here, is a change in what? Change in velocity. Now I'll just rewrite everything, okay? So I have delta x. I'm going to write delta x on this side now. V naught t plus 1/2 delta v times t, right? And if you recall, our definition of the slope of this graph, slope of v versus t graph, is equal to acceleration. And we call that A, right? So A is change in velocity divided by change in time. Now all of these quantities have direction. So I'm going to add arrows over all of them, okay? And this line, this in another color, the equation of that line there, slope of line, sorry, that's not what I meant, equation of that line in the form of y equals mx plus b it's going to be velocity, okay? This is the general equation of that line. Velocity equals, now the slope would be what? That's our acceleration. Acceleration times time plus our vertical intercept, initial velocity. So in physics, we use this equation quite a bit. I'm going to get this out of the way. Okay. Move this out of here. Clean it up a little bit. Whoops. Cool. So acceleration is change in v over change in t, the slope of velocity versus time graph. And that's what we have right here. In symbol form, I like to write this as final velocity equals A. Good symbol for time is just t plus velocity at 0 seconds. So this is a very useful equation that we use when we have constant velocity motion. Sorry, I said that wrong. Constant velocity? No. Constant acceleration. That's why there's an A term. And then we have an equation for acceleration. If you solve equation 1 for acceleration, you get your definition of acceleration. Okay? Or, likewise, if you take your definition of acceleration and you rewrite it, so if A equals change in V over change in T, change in V equals A delta T, okay? Change in V is V final minus V initial equals A T. I'm going to let T equal delta T, okay? T and delta T would be the same in this case. This is my delta T. Cool? So this equation simplifies to be V final equals V naught plus AT. So you can take either equation and create the other. You can always take your definition of acceleration and find your equation for velocity when you have constant acceleration. Okay? So I'm going to call this equation 1, your first kinematics equation. Now I'm going to do the same sort of thing over here with my equation for displacement that we got by finding the area of the rectangle plus the area of the triangle. Now I'm going to do a trick right here. I'm going to multiply by t over t, okay? So this is just multiplying by 1, but it's in a clever form. Let's rewrite this. Delta x equals v naught t plus 1/2 delta v over, now I can move my t over here, right? And I can even say that t is equal to delta t. I've already done that here. And then I'm going to leave this t as just a t. And when I combine them, I'm going to get t squared. Okay? So now when the dust settles, I have displacement. Oh, I need arrows over these things. I have displacement equals initial velocity times time plus 1/2. Oh my God. What is this? Haha. 1/2 a t squared. Beautiful. This is your second kinematics equation. Very powerful. And I'm going to call this equation 2. And I'll write a little 2a because if you change your delta x to x final minus x initial, after all, that's what delta x is, you can just rewrite your equation and get it in another form. I'll put arrows over everything. So all of these have direction. Final position equals, I'll move this term to the other side, x naught plus initial velocity times time plus 1/2 a t squared. So this is a nice little family of equations so far. Wait a second. Oh, this is cool. If I take this term, let me rewrite this. Final position equals 1/2 a t squared plus, that was nice, hee plus v naught times t plus x naught. Do you see it? This is a quadratic. Ha! This term here is your A term. This term here is your B term. This term here is your C term. So if you're ever in the unfortunate situation you have to solve for t, you can use the quadratic equation. Probably remember that. Anyway, there's another cool thing about this. This is very interesting. Our first equation was v final equals a t plus v naught, right? Ha! And the slope in your lab results, the slope of your VT graphs compared to the slope of your x versus t, which is the same, well, that doesn't have a slope, but this one had a slope, x versus t squared. Do you see? Do you see what happened here? This slope was double that slope. And this term is 1/2 a, whereas this term is a. This shows you why. That's kind of cool. So that was your second kinematics equation. You got one more to go.